So in the previous video, we actually proved to you that the symmetry concept, right? That stress tensor has a symmetry in it, and that this is somewhat some matrix that has 9 components, or 9 stresses in other words. Alright. Now if based on our stress tensor symmetry concept, we can actually change this particular tree into same as this tree, right? Because they are symmetry. And therefore this thing is equals to this thing. And therefore at the overall sector we have 3 stresses plus 3 stresses, and that this is equals to this, and therefore we have 6 stresses. Alright? In this video we hope to reduce these 6 stresses into a 2x2 matrix that has 3 stresses. Alright, this is 3 stresses because the stress tensor is still a symmetry. Alright, in order to do that, I have a space over here. This is spaced by a certain basis vector. Alright, they are all unit vectors, for example. Then we have a certain cube. If you still remember, this is a very big cube. And therefore this thing over here experiences this type of stresses, 6 stresses, because it's a 3 times 3. Alright? But as for plane stress, alright, which is what we're gonna do in order to have 3 stresses, so we're talking about plane stress assumption. And what we assume is that this length over here is very small. So small that relatively you are like this. Alright, way too small. We will have a sigma 22 and a sigma 11 only. Alright, and now therefore why is that this big surface area is so called what we are left of, is that sigma 33 is over here, the stress 33. If you remember, stress is equals to force over its perpendicular area. Alright, perpendicular area, I mean stress, meaning normal stress, I would say, to be more exact. Normal stress is equals to force divided by perpendicular area. And the perpendicular area, if it's this big, alright, you're gonna have a very small stress, right? Now, if let's say sigma 22 and sigma 11, their area is so small, and this is why when you divide by a very small area, you have a very large stress over here. And this is why we have sigma 11, sigma 22, sigma 12. I'll paste this here. Alright, so I have this one, I can also have this one, and I can cancel this one. How about explanation for sigma 12 and sigma 13 and sigma 23? How do I explain this? Remember, shear stress, for example sigma 13, is equals to force divided by its parallel area. Alright, shear stress is divided by parallel area, and normal stress is divided by perpendicular area. This is why, as I say. So therefore, if you were to divide by such of a big area, then what do you have? You have a very big force also, right? Sigma 13 is applying in this direction. It's applying on plane 1, and then plane 1 at the area of plane 3. I mean, I think you should get what I mean. It's plane 1 and its perpendicular area, which is this one. Alright, so as you can see by formula itself, this is very small. Alright, likewise for sigma 23, this is the shear forces acting perpendicular to its acting parallel to its area, and therefore the stresses is so low that we actually neglect. Okay? For stress 12 is acting on the stress plane 1. Alright, acting in the two direction, going in this direction. Alright, and therefore its parallel area is in fact this area over here, and therefore it's way too small, and therefore you have a very big stresses, and that not big rather than a stress that is something that we can measure compared to this path over here. Alright, I hope this is pretty clear. And therefore what we have, 2 times 2 matrix stress, alright, a plane stress. So we actually neglect that this is actually a very small x3 length. Prove to you that 6 stresses comes to 3 stresses, alright, which is this one. Now we can do for plane stress, we can also do for plane strain. This is the plane strain assumption, and in order to explain this, I can explain what is strain first. Strain is, for example, we have this rod over here. Alright, this rod has a certain strain, alright, certain changes in length. I call this delta, very small delta. Alright, and this delta divided by its own length, which is a certain percentage, will give us the strain. That is the definition of strain. So for example, if I have a very huge length over here, L0 is 1000, and that my changes over here is just 0.1, my strain is going to be way too small. And therefore, how do we apply this concept into our system right here? Alright, instead of this thing is so thin, alright, we can actually increase this all the way. Now we're gonna increase this length. Same thing, we have this cube. Now in order to analyze in terms of plane strain, we're gonna extend this length over here, or the area we can still keep the same. Alright, now we're gonna prove to you that we will eventually have this 2x2 matrix. And how do we cancel them off? Let's talk about strain 1, 1 first, using this formula. Strain 1, 1, alright, is at plane 1, stretching in the 1 direction, alright, and therefore it's going to increase by slightly a bit. This is delta, alright, and divided by its own length will give us a certain strain, alright. And if you take a look, this length compared to this delta, well, if you were to compare this to sigma 33, for example, sigma 33 is what? Sigma 33 is this length, I mean this plane pulling in this direction. So maybe I indicate in a different color. So the stretch with the same amount of delta x stretch, right? This is the same amount, delta x. This is in terms of this direction, the green color one, and the orange color is in terms of this direction, 3, 3. Right, as you can see, the difference is so big. The L over here for the green one is just this length over here, while my orange color one is way too long. So if this is the case, then divide this one divided by L, right, which is a very huge number of length, will give you a very small strain, right? On the other hand, in contrary, this length itself is way shorter than what is given over here, right? And therefore this length will somewhat be higher than your strain in this direction, alright? And therefore this applies to our plane 2 also, because we are just talking about this stretch over here, alright, going in this direction, alright. And therefore strain 1 and strain 2 we are keeping it, while strain 3 we destroy it. We do not want it, right? Because strain 3 has such of a big length that it will cause the strain to be so small. What about strain 1, 3 and strain 2, 3? 1, 3 is in plane 1, but you stretch in the 3 direction. So when you stretch about in the 3 direction, you are still going to talk about this system again. Alright, it's going to have a very huge length, and it's going to go all the way down. Alright, your strain will gonna go all the way down. You get what I mean? Because it's on the strain 1, stretch in the length in the direction of 3, and therefore you are stretching in this direction. And as for why the strain 3 is that you're talking about, for example, strain 3 in this case. Then you're talking about this plane, but stretching in also the 3 direction. So therefore the strain itself is quite straightforward for all systems, is that once you mention that you are going to stretch in this direction 3, this means you are going to stretch in this direction 3, and that's it. And therefore this applies to all of the other stuff, right? For example, if I were to stretch in the second plane, alright, but in the third direction, are you still going to have a change of delta in this direction, in the x3 direction that is going out or going down, which is this length, alright? So I hope that this is pretty clear, and therefore I would believe that this is quite straightforward for you already. 1, 2. You're talking about this plane stretching in this direction. So you're gonna talk about this thing. Alright, this little stuff. Alright, this length I should say is delta x. Alright, and therefore strain 1, 2 and strain 1, 2 they are symmetry, and therefore we have this thing, and this is actually 3 strains. Alright, so if you remember back multi-axial stress and strain, the triaxial system, this stress, right, is equals to C strain, right, and this C is the stiffness matrix for the 3 times 3 system. As you can see, becomes 6 times 6 now, right, because there is 6 stresses, right, because we know that the cube itself, the stress tensor of a 3 times 3 system, or in other words, this system over here is being reduced to 6 stresses, and these 6 stresses are being discussed over here, right? For the strain is equals to this is called a compliance matrix S, right, this whole stuff, and we know that it's inverse of C, correct? Because sigma is equals to C strain. If I were to have C minus 1 strain, if I want to find strain, I'll have this one over here, and this thing is simply, this stress is simply this, and this matrix over here is simply this, which is our compliance matrix. Okay, this is for a 3 times 3 system. What about 2 times 2 then? For 2 times 2, we have 3 stresses, which is over here, and this is our stiffness matrix, and this is our strain. And do take note that this is a gamma over here, alright, and it's being calculated in a different method. I think it will be this one, right? This should be like gamma 1, 2, I believe. I don't know, I'll leave you to think about it seriously, but I think in the future we'll get back to this one. Alright, but in the meanwhile, just take note of this thing, of this awareness, and therefore this thing is simply this one, the same thing. Alright, I mean this thing included. Alright, so as for strain, it's the same thing, because we have 3 strains, and therefore it's sigma 1, 1, sigma 2, 2, and sigma 1, 2 only. And this is the compliance matrix, is shown over here with all this chunk over here, and sigma 1, 1, 2, 2, 3, 3 is known as the stress. So sigma 3, 3 you can calculate through here, and I believe that sigma 1, 1 and sigma 2, 2 is given of certain values, while this is for the plane stress, sigma 1, 1 and sigma 2, 2, I think these values will be also given to you. I don't know, I'll leave you to think about it in the future. Now, as for pure torsion, is simply cylinder. Alright, you have a cylindrical system. Cylindrical system, you know that you will not be pulling this system in this manner. Alright, you will not be pulling this system in this manner. You're gonna twist it in this manner. This thing, one hand twists over here, the other hand twists over here, both direction. So if you take this plane and then you're going to translate over here, this is what it's talking. You're twisting in this direction and twisting in this direction, and also this thing, right? And should be this way and the other way. Or in other words, cylinder, you can twist in this manner and twist in this manner, or you can somewhat turn in this manner, although this is not recommended because you're gonna break your hand, but something of this manner. So you're gonna twist in this manner, or if it doesn't show much, not apparent to you, I'll just rotate this. Alright, this is a cylinder now. Instead of twisting in this manner, alright, now I'm gonna twist in this manner. Is this better? So you're somewhat breaking this in this corner over here. For this pure torsion, this sigma 1, 2 is equals to Tc over J. Alright, since we know that there will be no normal stresses, so these are all zeros. And sigma 1, 2 is just pure torsion. Alright, so pure torsion, the T is simply the torque force times its perpendicular distance, while the C itself is the diameter over 2, the diameter of the cylinder, and then the J is equals to pi over 2 C4, where C4 it's, you know, D over 2 and then to the power of 4, or radius 4, something of that meaning. Further reduce what we have done in the previous, the stress strain stuff, that is 2 by 2 2x2 stuff. If you remember, 2x2, it's this one, for example, you actually reduce it to only one pure torsion, one stress only. Alright, you can reduce a beam in bending from its 2x2 matrix to a 2 stresses, sorry. So instead of 3 stresses, we have 2 stresses. But because this force is acting downwards, alright, you only cause stretching and also shearing. That's all. Alright, you're gonna shear in this manner only. While shearing, you're gonna somewhat stretch this thing over here. So the forces will create this phenomenon. This phenomenon will actually bend the beam. Alright, and therefore this phenomenon is only in this direction, stretching, and that has really no meaning in terms of why this one is 0, because if your forces is acting on this side, then sigma 1 it will be 0, then we have something like sigma 2 over here. This sums of the meaning, but I just want to convey that you can actually simplify a certain system, alright, all the way, and assume certain stuff, and all the way you can simplify until such a small little matrix to solve, which can take a lot of inefficient time away. And for the next video, I'll just talk about types of loading very fast, so it will be a very short video just to raise awareness in terms of the content. See you there.